Hi guys, my name is CETT. I am from course Network Security Semester 4. Today I gonna discuss with you guys about the transform coding. I gonna give you guys a quick overview what is transform coding. Transform coding uses transforms to obtain representations of signals that aid the compression. Transform represent the signal in frequency domain. We know that human perceive signal in only a narrow bands of frequency. Spatial frequency is in case of the image, and then we have another which is temporal frequency in case of audio. Alright, now I'm gonna show you guys about the visuals of the frequency. Okay guys, and this is one of the example of the spatial frequency that I just mentioned before. Okay, this is the what you call the graph, and the graph it got the crest, and then you got the trough, and then you got the midpoint. Okay, and the crest indicates the maximum brightness level, while the trough indicates the minimum brightness level. Just same as these gratings, like when the trough is indicates the minimum brightness level, right? So it will become dark. Okay, just same as this when the trough and then your minimum brightness level. As for the crest, it indicates the maximum brightness level, so it's like don't have any dark spot. Okay, now okay, the grating consists of the bars of the alternate brightness. If we see closely, this is just like the before that one. It's like got 3 bar, black bar, and then when we see closely, it's closely related to what we can see or interpret by our eyes, which is an E by adding a black bar at the upside here. So this become an E. Okay, I'm gonna talk about the grating just now. In our retina contains of a cone cell, and then this is job by detecting the brightness level at particular spot. The cone cell detect a bright spot at it, and it is turned on, and then it will create a neural signals, and vice versa if the cone cell does not detect any bright spot. The mechanism allows the retinas to detect gaps by gauging the brightness across the targets. If the gaps is too small for the cone cells to resolve, the eye will see the grating as a dark solid objects. This is when your eye reaches a resolution limits. Okay, now I'm gonna show you guys about another frequency called temporal frequency. Okay, this is the temporal frequency, one of the example. The temporal frequency is the number of occurrence of a repeating event per unit of time, and you can see from the below we have the amplitude and then the time. So is this temporal frequency is for the case of the audio. Transform allow us to find the representation of signal with the correlations of the structures, which most of the signals is compact into few components. Transform of these signals is in frequency domain, which result in compaction. How we work in the transform domains to obtain the compression. First of all, we need to turn our attentions on the transform coding process. First of it, which is consists of the transform of data into the transform domain. Second is the quantizations of the transform coefficient of data in the domain, and then coding of the quantized coefficient. Because of the transform coefficients contain different amount of energies, informations, perceptual importance, we need to allocate resources in case of bits based on their relative importance. Okay, now we're gonna start with the introduction. For a Gaussian source, the differential entropy is given as 1/2 log 2 pi E variance. An increase in the variance result in increase in entropy, which is the measures of information contained in the source output. to begin with this discussion, we're gonna consider one of the examples that I gonna show you guys next. Okay, this is the example that we just mentioned before. In the table, we have the original sequence which contain the height and weight. We use the height and weight as a coordinate point in the two-dimensional space sequence which shown graphically at our right hand side. And the output value tends to cluster around the line y equals to 2.5x. Okay, we can rotate this set of value that tends to cluster around the line y equals to 2.5x by transformations formula, which is transform sequence equals to A matrix times the x, where x is the two-dimensional source output vectors. Okay, and this is the x. x0 is the height from the table we have, and x1 is the weight. And then we have A is the rotation matrix. The rotation matrix is this: A equals to rotation matrix like cos, sine, negative sine, and cos. And the symbol, this symbol is the angles between the x-axis and the y equals to 2.5x line. Right, next we will continue with this. This is the transform sequence. We have coordinate 1 and coordinate 2 of the transform sequence. It is rotate or transformed set of value. For this particular case, matrix A is this one. This is the matrix of A's. By using the previous the formula we mentioned before, and we get this. After that, we use this. Okay, we use the formula. Then we have the matrix A times the x. This is the original sequence that we have the height and the weight. And then after that, we'll get 1.181, 0.98, 2.78, and we will round it into the nearest numbers, and then we can get the result of this. Okay, this is the transform sequence table that we obtained from the original sequence by using the formula that I just mentioned just now, and then we get these coordinates. Seems like the first coordinate is significantly bigger when being compared to a second coordinate. And we use these tables to plot a graph. We get the graph like this, and then we noted that the original value, the transform value tends to cluster around the line of 0. And note that we rotate the original values by an angle approximately 68 to the transform value, which is all these clustered transform value. Suppose that we set all the second coordinate to 0 in the transform sequence. In this case, this reduced the number of elements that needed to be encoded by half. The effect of throwing away the half sequence can be found out by taking the inverse transform of the reduced sequence. Inverse transform consists of reversing rotation, and this can be done by multiplying the sequence with element of each block, that is with the second element of each block that is set to 0 in the matrix. Okay, about the reverse transform that we just mentioned before, we can use the transform matrix, the reverse or inverse matrix times with the transform sequence where the second element is being set to 0. And then we can get the reconstructed sequence following reconstructed sequence, and the reconstructed sequence is very close to the original. The reason there is so little error introduced in the sequence of the original is that for this particular transformation, the error introduced into the original sequence is equals to the error introduced into the transform sequence. That is, we have this formula. Okay. The error introduced in the transform sequence is the sum of the square of the sum of the squares of the transform sequence that are set to 0, the magnitude of these elements are quite small. Therefore, the total error introduced into the reconstruction sequence is quite small. By discarding the second pair with less information, we can reduce the number of samples that we need to be coded. Most of the information contained in each pair is put into one element of each pair. The other pair can be discarded easily without significant effect due to their less information in it. We can extend the ideas to a longer block of data by compacting most of the information into few elements of the transform sequence. Using a reversible transform, we can discuss the elements of sequence that contain not much of information, and this is the basic idea of transform coding. We can get the maximum number of compaction if we use a transform that decorrelates input sequence. That is, samples to sample correlation of transform sequence is 0. All transforms are linear transform, which means that we can get the transform sequence from the original sequence. And the characteristic of the elements in the transform sequence are determined by the position between the sequence. Just like the previous examples, we get that the first have a biggest, the first of the transform sequence has a biggest value, while the second has a lower value, but we can make such general statement. The measuring of differing characteristics of the different elements of the transform sequence is based on the variance and the information of each element's container. Okay, this is the transform sequence, and then the original sequence can be recovered from the transformed sequence via the inverse transform, which is this. The transform can be written in matrix form. This one and this one, they are transformer that I just mentioned above this. Okay, and then where A and B are n plus n matrices, they have I and j elements of matrix is given by this. The matrix can be written as the left hand side and the right hand side is written just like the sequence up there, which is beside there, right? B, A, N, right? And then forwards and inverse transform matrices A and B, they inverses each other. That is, A, B, B, A equals to identity matrix. They are same matrix. Okay, below this, just like the two transform that I mentioned before, the up there, which that we just mentioned, and then two of these equations, they deal with the transform coding of one-dimensional sequence, which is the sample speech and the audience sequence. Transform coding is very popular for the image compression. Take advantage of the two-dimensional nature dependency in the image. We look into the two-dimensional transport. Okay, like this, let the xij be the ij pixels in an image. A general linear two-dimensional transport block size is like this. Okay, and then the two-dimensional use are separable transform. What does this mean by separable transform? That is, we can transform a two-dimensional block by first taking the transform coding first by taking the transform along one direction, then repeating the transform in another direction. In terms of matrices, involve taking one directional transforms of rows, then taking the column by column transform of resulting matrices. Okay, now we're gonna look about the reverse operation that we can be doing. We will first take the transform columns, then take the row by row transform of the resulting matrices. And then below this is the transform operation, and it's represented by this. It's a bit of differ from the upstairs that we mentioned. Okay, now we have the matrix terminology for this one, which is matrix terminology represented by matrix terminology, which is this one, A times A transpose. The inverse of this is like X, B, this one, and B transpose. Okay, and then we will talk about the autonomous transform. Orthogonal transform has a property that inverse matrix is simply its transpose. For example, like this, we have like B, right? B is equals to A minus 1 and A transpose. It's like directly inverse is like simply its transpose. Same as the just this one, X A transpose A is same like this. Okay, like this. B, right? B is inverse of B is B transpose. Inverse of B is A transpose, right? So this one becomes A transpose. Then the inverse of the B transpose is A, right? So it's changed to A. Most transform are energy preserving. Sum of the square of the transform sequence are same as the sum of the square of the original sequence. This can be seen by this one. This is the sum of the square of the original sequence, and as we go through this, that is if E is expanded out. If A is an orthonormal transform, the ATA will become identical, so there's cancel out. And then after that, we can see that we in the result we form the sum of the square of the original sequence, and this shows that the sum of the square of transformed sequence are equal to sum of the square of the original sequence. And later on, we have a way of measuring the energy compaction in a transform is using a GTC's formula, this formula, okay. And then we will look into another example. If we have like two-dimensional orthonormal transformer A, the inverse transform can be written as like this. And then we have said transform value are coefficient of an expansions of input sequence in terms of the rows of matrix. The rows of the matrix are often referred to as basic vectors of transform, as they form an autonomous basic sets, and elements of the transformer sequence are often called transforms coefficients. We will talk about the outer product of a transform. For an n plus n transform of A of the matrices that we have been used in the previous example, we let the Aij be the product of I and the j row. Then the previous matrix, this is how we get the outer product. We times 2 of this 1 over 2 at times 2 of it, but this will change into like a vertical and then horizontal and then negative 1. It's like 1, 2, 3, 4, negative 1, negative 1. Then we will get a product 1 over 2, A00, A01, A10, and A11. After that, we will see the inverse transform is given by this formula. This formula, why we get 1 over 2? Because the 1 over square of 2, 1 over square of 2 times together get 1 per 2. And then why do we still have the same matrix when it's transposed? Because when we transpose the original to a new, there is no difference, and at last we'll get our products of this. Why do we have A00, A01, A10, A11? Because this is their outer product, so we will add it into the result or the answer. And then the transform 00 is the DC coefficient, which known as direct coefficient, does not change with time. As for the others, it's known as the AC coefficient, and it does change with time. As for the A00, it will be the DC designation, because all elements of basic matrix A00 are the same. Hi guys, that's all from me, and then the other parts of the transform coding will be discussed by my friends. Thanks you guys for watching. Bye.
Going to continue about the transform coding. In transform coding, there are many transform will construct to the specific data, but in transform of interest, to find out the best what we can do with the transform coding in order to find the best performance available. There are many transform in it, but one of it is the DCT. So what is the DCT? Okay, so let's get started. So what is the DCT? DCT stands for the discrete cosine transform. So with this, now we have the idea that we are doing the transformation of an image. Transformation of an image. Suppose I have an image, let's say F. This image is the spatial domain. Important. Every image is a spatial domain. If I can convert the spatial domain into the frequency domain, I'm doing the transformation. Got it? Okay, I can do this I can do the transformation using the DCT. And if I want to do the transformation other than DCT, we can use the DFT. So what is the difference between the DCT and the DFT? Okay, for the DCT, it is a for the DCT, it is a real term. But for the DFT, it is a complex term. Go to see the notation. Okay, for the first dimension image, if I have the spatial domain, let's say fx, and we apply the transformation, we get the frequency domain fu, let's say. So we get the frequency notation of the frequency domain of fu. Okay, for the two-dimensional image, let's say we use the f x y, and we apply the transformation also. We also get the FUV. Okay, for the FUV, the FUV is also the frequency notation of the domain. For the FXY ni, any pixel can be used for the example for the spatial domain. Okay, so how we can get the transformation from spatial domain to the frequency domain for this? So in other words, how can I apply the DCT and achieve the FUV? So let's take a look at the one dimension and two dimension. For the first dimension, we have the FU, and for the second dimension, we get the FUV. Okay, so how I can find the first dimensional and two dimensional F? Okay, for the one dimensional F, we use the C multiplied by the original image for the first dimensional. For the two dimensional, we use the C times the original image times the C transpose. Okay, so what is the C is stand? C is for the cosine transform matrix. And the formula we use for the search for, so, and the formula used for the DCT is the C UV equal to square root 1 over n, U equal to 0, and V less or greater than 0, and V is greater than for 1 for the first rule. And second, we use the square root 2 over n cos 2V plus 1 pi U over 2n and u is less or greater than 1 and u for the v is greater than 0 and v is less or greater than m for 1. Okay, when u equal to 0 means the first row, that is for the matrix, example this matrix. Okay, for u is this and v is this, it start with 0. When we talking about u equal to 0, it refer to the first row. That means example for the matrix when u is down and v is side. Okay, for the first row, when u equal to 0, it is the first row. The first row, that means this row, and until it's reached for n minus 1. Let's look at the example. Okay, for n equal to 4, when the c u v, okay, first construct the matrix like this. When it's 4, it mean when it start with the u, it mean 0 1 2 3. Okay, when n equal to 4, it means that it has 4 value, but the formula is using the u equal to 0, so it must start with 0. So 0 1 2 3. Okay, this is for the u, and for the v the same also. For we can write down 0 1 2 3, and for the first row we are using the 1 over square root 1 over m formula. So square root 1 over 4, we get the 0.5. So for the first row, that for the 0 row, we list down the 0.5 value in the matrices. Okay, next for the row 1, we search the value for the matrix by using the second formula here. So we will get the 0 4 5 3 and the 0.2705. Get this value, then draw a line between the 0 1 and 2 3 like this, because there will be trick to do this matrices easily. Okay, after you this for this row, it just like mirror from the row 0. So just copy the equation from row 0, that is 0.5 0.5 0.5 and 0.5. Okay, for the equation 1, it's just like a mirror, so just copy this into this and this into this. Okay, that will be this 0.2705 and this will be the 0.653. Okay, the next trick for the row 3 is this also like a mirror. So this will become come to the row this, and the 0.2705 will come to the row of this. So we can see this like this. So we just write the equation again in the matrices like this, 0.275 and 0.653, and the same with this. Okay, after this there will be a final step for this, but let me move it to a new page for a better understanding. For the final step, first by using this value, first you make a circle first, then draw a arrow for like this. like this. So this means that the indicate arrow line show that the value the next value will be negative. So this value will be negative, 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 and this value will be negative. So then you will get the new matrix that consists the value of n. With this, you will get the final answer for the matrices of the DCT. Okay, so let's talk more about the DCT point. Firstly, C is not equal to the C transpose. That means it is not a symmetry matrix. Second, the DCT is the real and orthogonal. The third is DCT also is one of the JPEG comparison. The JPEG comparison, it is also the advantage when we using the DCT. And the fourth point is DCT is a sinusoidal function. That is, for the graph, it will be like this. That is different to the DFT. Then we also get the quantization and coding of transform coefficient. So let's take a look about it. For quantization and coding of transform coefficient, if amount of information conveyed by each coefficient difference, it makes sense by assign different bits to different coefficient. Two approaches can be used to assign bit. That is, first, based on the average properties transform coefficient, and the second is we assign bit as needed by individual transform coefficient. So how we use this first approach? That is, first we obtain estimate of variance of transform coefficient. This estimate used by one of two algorithms to assign number of bits to quantize each coefficient. That we can assume relative variance of coefficient correspond to the amount information contained in each coefficient. That means the higher the variance, the higher the bits. For distortion, find the bit allocation for minimize the distortion by use the method language. For the formula, we can use the R equal to 1 over M, sigma M equal to K equal to 1 RK. That is, the R represent the average number of bit per sample, M represent the number transform coefficient, and the RK represent the average number of bit per sample used by the KIT coefficient.
Hello and Assalamualaikum everyone. From the previous video, I told about the application to image compress, which is JPEG. Okay. Today I will discuss with all of you about the application more detail. Before we go more deeper in this topic, let's discuss about the application first. Okay, so for your information, application to image compress is one of the LUQMAL image compression. Okay, transform coding approach using DCT. This is a little bit about the image application to image compression. Okay, we continue our video. So the input image is first level shift by 2 the power of p minus 1. So we subtract 2 the power of p minus 1 from each pixel value, where the p is the number of bits used to represent each pixel. So if we dealing with 8-bit image whose pixel takes on value between 0 to 255. So we should subtract 128 from each pixel to that the value of the pixel varies between negative 128 until 127. Okay, so we divide the image into block of size x times x, which are then transformed using x times x forward to DCT. Okay, then any dimension not multiple of 8, the encoder will replicate the last column or row to get the final size multiple of 8. So the replication of the column and the last column and row will remove during the decoding process. Okay, in this topic we should know about we need to notice that the lower frequency coefficient in the top left corner on the table have larger value than the higher frequency coefficient. Okay, that's all. Okay guys, let's continue to our next subtopic, which is quantization. JPEG algorithm use uniformly thread quantization to quantize the various coefficients. Quantizer step size organized, we call it as quantization table. Quantized value represented by a label. Label is corresponding to quantized value obtained based on the formula given. So I will show you the formula after this video. We should know about the reconstructor value. We should know about the formula. The formula for reconstructor value is label. The label we should time with the corresponding entry. Okay, we continue. The step size generally increase as we move from DC coefficient to higher order coefficient. Because the quantization error is an increased function of the step size, more quantization error will be introduced in the higher frequency coefficient than lower frequency coefficient. Quantization error in DC and lower AC coefficient more easily detectable. Okay, the coefficient plus magnitude less than half corresponding step size, this will set to the 0. Step size at tail end of zigzag scan increase, probability finding a long run of zeros will increase too at the end of scan. The step size increase to reduce number of non-zero value need to transmit. Okay, step size reduce number of non-zero value translate reduction in the number of bits that need to transmit to. Okay, we go to the next subtopic, which is coding. The famous person in this coding of application to image compress is Chen and Pratt. I'm sorry. Okay, they're using Huffman code, which encoding the label of each coefficient and the number of coefficient since less non-zero label. JPEG approach DC and AC coefficient coded differently. So DC coefficient is constant metric. So some multiple of average value in x times x blocks. First block with the neighboring block x times x block average pixel value not differ substantially. Okay, the label is coefficient B closure. Encode the difference between neighboring label rather than encode label themselves. Encode pixel value depend on the number of bits. Larger alphabet quite unmanageable, so JPEG recommend the partitioning possible value. The different take into category as growth power of 2. For the example, category 0, the number of member is 1, which is 0 only. No additional bits to specify the value. In category 1, 2 members, which is -1 and 1, need 1 bit take on the encode to specify the particular element. Next example is category 2, which is have 4 member. The member is -3, -2, +2, and +3. Okay, different size will affect different number of bits that can identify value of each category, and the number of zero value labels Z, since the last zero label from a pointer to a specific human code as shown in table. I will show you at the end of this video. If the label being encoded falls in category 3, 15 zero value label prior to this non-zero label in the ZZ scan. Then we form the pointer f/3, which point to the code word as below. Okay. Because the label fall into the category 3, we follow this code word with 3 bits that indicate which of the 8 possible value in category 3 is the value that the label takes on. Specific code in this subtopic, which is EOB, stand for end of block. End of block is last non-zero value along ZZ scan. The second is ZRI code, which is the number of consecutive zero value along the ZZ scan exceed 15. Okay, next, DC coefficient is coded by taking first DC coefficient is coded by first taking the difference between first the value of quantized label in block and with the previous block. Encode AC coefficient is using order using ZZ scan. Okay, for example, value 1 category 1 based on the number given. Okay, value 1 no 0 transmit to Huffman code corresponding to 0/1. So the single bit 1 indicate the value being transmit is 1, not -1. The next number is -9. So -9 is category 4, 7th element. Then the send binary string 1011 and the Huffman code is 0/4 followed by 0110. The next is number 3, category 2, Huffman code 01 corresponding to 0/2, and then the next number is 0 sent to EOB Huffman code 1010. Okay, DC coefficient 2 bits long, grand total of 21 bits represented by x times x block is an average, so the average is 21/64 bits per pixel. Okay, then reconstruction. For the reconstruction, they use dequantization. So what the dequantization do? They using the inverse transform, which is we need to plus 128 to the reconstruction table. 8 bits represent 9/32 bits per pixel, which is close to original. Okay, so what we need to do to accurate the image to close original. So we need to do at cost of n increased bits. We need to time which step size in quantized table, and then to use step size we need to multiply with the number is greater than 1. So these two method is reduced in bit rate at the cost of increased distortion. Okay, that's all in the coding subtopic. Subtopic in the application to image compress, which is the format. The most common format used for storing JPEG encode image is the JPEG file interchange format, which is stand as JFIF. It is used a subset of the marker specified in the JPEG standard to partition the bit stream. Marker are assigned a 2 bit, which the first byte being FF. The second byte of the marker code is neither FF or 0. The marker also can be standalone. For example of these are the SOI stand of image, which initiate all JFIF file, and EOI file marker, which terminate all JFIF files. Other marker act as header for payload, the first 2 bytes of which encode the length of the payload. Example of the marker include application specific APP0 marker, which immediately follow the SOI marker and has the following format. Okay, the optional element include table marker such as DHT and DQT. DHT is defined Huffman table, and the DQT is defined quantization table. The syntax for the DHT marker the syntax of the DHT marker is after 2 bytes that contain the length, the most significant 4 bits of the next byte indicate whether the Huffman code belong to DC coefficient or AC coefficient. The number of Huffman code word of length 1 through 16 are stored in the next 16 bytes. Okay, DQT is defined quantization table. Okay, the syntax is most significant 4 bits to specify whether needs to store 1 or 2 bytes. 0 indicate a single byte used for each quantization value. 1 indicate 2 bytes. Next 64 bytes or 128 bytes contain 64 quantization table values stored in zigzag scan. Okay, the optional table marker segment followed by frame header to indicate start frame, so they can can be followed by number of scan. New scan begins with DNL marker segment. So DNL marker segment is defined number of line net scan. Then they reset the dimension of image original. Scan begin with optional table that scan the header. The header first 2 bit is start of scan as marker. They based on the number. Okay, the first 2 bytes in the scan header is to start of scan marker, followed by the length, number of component and the component parameter. The header is followed by the entropy code data interleave with restart marker DRI. The marker provides a degree of robustness to the JPEG data stream. One of the drawbacks of using variable length code is that bit error tend to propagate. The DRI marker prevent the error from propagating beyond a restart interval. The file is terminated with end of image EOI marker. That's all from me. Thank you.
Hello guys, my name is Akmal. Today I'm going to talk to you about JPEG ST. Okay, the JPEG ST standard was introduced in 1992. Since then, there has been a huge amount of development in both image generation method and the ubiquitous of both digital cameras, mostly in cell phone. And digital image, there have been a number of attempts to replace the original JPEG standards. The most prominent of which is the JPEG 2000 standards, while the JPEG 2000 standard has carved out a niche of its own in digital movie compression and the compression of medical image. In everyday consumer application, the original JPEG standard will still reign, if not supreme, at least as the dominant player. A major reason for the failure of the newer standards to unseat JPEG has been the lack of backward compatibility with JPEG decoders, or more specifically, decoder using the JFIF format. JPEG ST has tried to avoid this trap by generating a bitstream which is compatible with JFIF. The goal of JPEG ST is to offer support for the high bit depth image generated by many cameras and allow the compression of high dynamic range image. The way they do this is rather simple. The high dynamic range is image compressed to generate to image, a low dynamic range image or base image suitable for compression with the JPEG algorithm, and a residual or extension layer which is also encoded using the JPEG algorithm. There are several ways in which the extension layer can be generated. The standard only specifies how the high dynamic range image is to be generated given the base layer and the extension layer. But there is an embedded assumption that the base and extension layer will obtain from the high dynamic range image in one of several ways. To understand the various parameters, consider figure above, which shows a simplified possible way in which the low dynamic range and extension layer could have been generated. 311. The low dynamic range image B is simply a tone map. A high dynamic range image which after color transformation is encoded using the baseline JPEG encoder. The extension layer is generated by the subtracting the tone map from the high dynamic range image, normalized by a scale factor which is a functional of the luma component of the extension layer. In the profile A, transformation above is the function of the luma component. Symbol A is the inverse tone mapping function, and C corresponds to the color transformation. Following the lower branch, E1 is the extension layer with luma component set to 0, is the inverse color transformation, and VI is a scaling function. In profile B, the pixel of the high dynamic range color component are generated from the pixel of the lower dynamic range image and the residual image by where symbol BI is an image dependent gamma correction. A simplified encoder is shown in figure above. In profile C, the HDR image is also generated component wise. where symbol C is implemented as a lookup table and the shift makes the essential image symmetric around 0. A possible corresponding encoder is shown in figure above. The implementation of profile C can be made lossless, allowing for lossless compression in JPEG ST. Okay, the next I want to talk about is overlap transform. As mentioned in the previous section, the use of the block-based transform has the unfortunate effect of causing distortion at the block boundaries at low rates. A number of techniques that use overlapping block have been developed over the years. In the following, we briefly look at the two applications to overlap transform, one to audio compression and one to image correspondence. Okay, the next topic is the application to audio compression, the MDCT. An application of overlap transform that has gained wide acceptance in audio compression is a transform based on the discrete cosine transform called the modified discrete cosine transform. It is used in almost all popular audio coding standards from MP3 to AAC to OGG, Vorbis. The MDCT used in this algorithm use 50% overlap, that is, each block overlaps half of the previous block and half of the next block of data. Consequently, each audio sample is part of two blocks. If we were to keep all the frequency coefficient, we will end up with twice as many coefficient as samples. Reducing the number of frequency coefficient results in the iteration of distortion in the inverse transform. The distortion referred to as time domain aliasing. The reason for the name is evident if we consider that the distortion is being introduced by subsampling in the frequency domain. Recall that sampling at less than the nucleus frequency in the time domain leads to an overlap of replicas of the frequency spectrum of frequency aliasing. The lap transform are successful because they are constructed in such a way that while the inverse transform of each block results in time domain aliasing, the aliasing in consecutive blocks cancel each other out. Consider the scenario shown in figure above. Let's look at the coding for block I and block I plus 1. The inverse transform of the coefficient resulting from both these blocks result in the audio sample. In the subblock Q, we assume that the block size is n and therefore the subblock is n per 2. The forward transform can be represented by n per 2 times n matrix. B. Let us partition the matrix into 2n over 2 times n over 2 blocks A and B. Let S1 P Q, then the forward transform PS1 can be written in terms of the subblocks as the inverse transform matrix Q can be represented by n times n per 2, which can be partitioned into 2n per 2 times n per 2 blocks C and D. Applying the inverse transform, we get the reconstruction values S. Repeating the process for block I plus 1, we get to cancel out the aliasing in the second half of the block. From this, we can get the requirement on the transform. Note that the same requirement will help cancel the aliasing in the first half of block I by using the second half of the inverse transform of block I minus 1. One selection that satisfies the last condition is where J is the counter identifying matrix. The forward modified discrete transform is given by the following equation, where Sm are the audio sample and Sk are the frequency coefficient. The inverse MDCT is given by, or in terms of our matrix notation, thus, while the inverse transform for any one block will contain aliasing by using the inverse transform of neighboring blocks, the aliasing can be cancelled. Okay, the next topic I want to discuss is about the application to image compression, JPEG SR. The JPEG SR is a standardization of the proprietary standard Microsoft HD Photo. It can handle a much greater bit depth in the image, 32 bits as opposed to 8 bits per color for JPEG. The image is divided into tiles which can be decoded separately. Each tile consists of an integer number of microblocks, which are blocks of 16 times 16 pixels. Consider the microblocks shown in figure above divided into 4 times 4 blocks, which will operate on by the core transform. The overlap transform also operates on 4 times 4 blocks when it can, which is mostly in the corner of a tile and 2 times 4 or 4 times 2 blocks on the edge of a tile, as shown in figure 2 here. We are assuming that the tile consists of a single macroblock. The transform coding process is a two-stage process. In the first stage, the 4 times 4 blocks are transformed using the core transform. In the second stage, the DC coefficients for each macroblock are collected together. The macroblock size being 16 times 16, this means we end up with a 4 times 4 block of DC coefficient for each macroblock. These coefficients are transformed using the core transform. This process of decomposing the low frequency components of an initial decomposition will become more familiar when we look at subband and wavelet based compression. The overlap filtering or the POT can be applied in 1 or 3 different ways. It could be applied only prior to the first stage, it could be applied prior to both stages, or it could be applied to neither stage. Usually the first alternative provides the best performance. In each macroblock, after the first stage, there are 256 coefficients, 16 DC coefficients and 240 AC coefficient. These 240 AC coefficients are referred to as the high pass coefficients. After the second stage, the transform of the 16 DC coefficient results in 1 DC coefficient and 15 AC coefficient. These 15 AC coefficients are referred to as the band pass coefficient. The 3 different bands, DC, band pass and high pass coefficient, are each quantized with a different quantization, which is selected from 1 up to 16 quantizers, which are encoded as site information. This quantized coefficient can further be predicted from neighboring blocks and the prediction residuals encoded using adaptive entropy coding. Okay, that's all for me. Thank you.